All right, let's dive deep, right into the heart of the atom. We're going to explore the incredible forces that will literally shape our entire universe. This is all about the unstable atom and its constant epic quest to find a little bit of peace. Okay, so here's a question for you. What could a billion-year-old rock possibly have in common with the blazing sun? I know, it sounds like a riddle, right? But the answer is actually the same exact physical process, something happening on a scale so tiny we can't even imagine it. So, the main character in our story today is the atomic nucleus. But here's the thing, not all of them are created equal. A lot of them are, well, they're just not stable. They've got this imbalance of energy and particles, and it puts them on this relentless journey, this quest to find a more stable, more chilled out, lower energy state. So, how does it do it? How does a nucleus finally get stable? The answer is something called radioactive decay. Now, this process is totally random and spontaneous. And what spontaneous means here is that it just happens. No outside push needed. It's the universe's own built-in fix for instability. Turns out, this whole quest for stability isn't just a one-lane highway. There are a few different paths an atom can take. So let's check out exactly how these unstable nuclei manage to transform themselves. Okay, so an unstable nucleus basically has three main tools in its toolbox to get rid of that extra baggage. First, it can shoot out an alpha particle, which, is basically just a helium nucleus. Or it can fire off a beta particle. Think of it as a super fast, high-energy electron. And finally, it can just release a gamma ray, which is just a pure, powerful blast of energy. All right, let's really dig into this table because this is where it all clicks. First up, check out alpha decay. The nucleus tosses out a helium nucleus. And what does that mean? Well, you can see right there, it loses 2 protons and 4 total particles. And here's the mind-blowing part, it literally becomes a different element. Now, beta decay, this is where things get a little weird. The nucleus spits out an electron. But wait a second, how is there an electron inside a nucleus? Well, what happens is a neutron suddenly decides to become a proton and an electron. The brand new proton stays put, but that electron gets launched out at incredible speed. So look at the result. The proton number actually goes up by 1. It changes into another element again. And finally, you've got gamma decay. Notice how nothing really changes in the particle count. The nucleus is just letting off steam, releasing a burst of pure energy to chill out. It's kind of like the atom just taking a deep breath and relaxing. And you know what's so cool about this? All of this decay happens at a super predictable rate. And that brings us right back to our ancient rocks. Think of it like a cosmic clock. We can look at a rock and measure how much of the original uranium-238 is left compared to how much has turned into stable lead-206. And by checking that ratio, geologists can figure out how old that rock is, and even how old the Earth itself is. Pretty amazing, right? So, everything we've talked about so far, natural decay, that's a pretty passive process. The universe just does its thing. But what happens when we step in and decide to force the issue? Well, that brings us to 2 of the most powerful, most dramatic reactions in the entire universe, fission and fusion. Okay, so let's get this straight. You've got the 2 heavy hitters here, and they're basically polar opposites. On one hand, you have fission. That's all about breaking apart. You take a big, heavy nucleus like uranium-235, and you split it into smaller pieces. Then you've got fusion. That's all about joining together. You take 2 really light nuclei, and you force them to combine into a heavier one. Totally different actions, right? But here's the wild part. Both of them release just a staggering, unbelievable amount of energy. But there's a pretty big catch, and it's all about how you get them started. Fission, it turns out, is relatively easy. All you really have to do is smack a uranium nucleus with a single neutron and boom, it kicks off. Fusion, though, that's a whole different ballgame. To get those light nuclei to fuse, you have to overcome this massive force of repulsion between them. And to do that, you need absurdly high temperatures and pressures. I'm talking about the kind of conditions you'd only find in the core of a star, like our sun. So that brings up a huge question. All this energy, where does it actually come from? It really seems like it just appears out of thin air. The answer, it turns out, is hidden in a really strange phenomenon. And it was unlocked by probably the most famous equation in the history of science. You see, when scientists looked really, really closely at these reactions, they found something bizarre. If you were to weigh all the particles before the reaction and then weigh all the pieces after, the after pile is always just a tiny bit later. There's missing mass. They call it the mass defect. So, what's going on? Where did that mass go? And this is the answer. Einstein's E equals mc squared. It's so famous, but what does it actually mean? It means that mass isn't gone. It's not lost at all. It's been converted, transformed directly into pure energy. And let's really wrap our heads around this. E is the energy that's released. M is that tiny little bit of missing mass. But c, that's the speed of light. And it's not just c, it's c squared. The speed of light is already a ridiculously huge number. When you square it, it becomes astronomical. So you're taking that tiny sliver of mass and multiplying it by this incomprehensibly massive number. That's the secret. That's why a single nuclear reaction releases millions of times more energy than a chemical reaction, like, say, burning a log. It's the universe's ultimate exchange rate, and the payoff is gigantic. Okay, so this isn't just some crazy abstract physics equation. This idea, converting mass into energy, has completely changed our world. So let's bring it back down to Earth and see how we actually use these atomic reactions to, turn on the lights. Believe it or not, at its heart, a nuclear power plant is really just a super high-tech way to boil water. It's actually pretty straightforward when you break it down. First, you get a controlled fission chain reaction going with uranium-235. That reaction creates an incredible amount of heat. Next, you use that heat to boil water, turning it into high-pressure steam. Then that powerful steam pushes against a turbine, making it spin like crazy. And finally, that spinning turbine is hooked up to a generator, and that's what makes the electricity we use every day. It's all about converting that nuclear energy into something we can actually plug into. So we've got fission working for us here on Earth. But what about fusion? Well, fusion is what powers, the entire cosmos. Every single star you see in the night sky, including our very own sun, is basically just one gigantic fusion reactor. They're all constantly smashing light elements together to make heavier ones, and in the process, releasing all the light and heat that makes life possible. And that really brings us to the big final question. Fission is powerful, for sure. But fusion is the holy grail. It promises near limitless amounts of clean energy with very little waste. The only problem, the massive challenge, is that to make it work, we literally have to recreate the conditions inside a star, right here on Earth. So the question that will define our future is, will we ever truly be able to bottle the sun?